Finally, we come to the most important kind of regression model that is the heart of our textbook and of the course that we have in the book. These are hierarchical models. They're sometimes called linear mixed models. Sometimes they're also called multi-level models. They're all basically the same type of model. You might have seen this in using the Elmer function in R. It's a very famous class of models. And these are very standardly used models in psychology and in linguistics and many other areas where you have repeated measurements of data, right? That's the critical thing, that this kind of model deals with repeated measurements, right? So an example that I will work with quickly is an example of an EEG experiment, electroencephalography. What we are doing here is that this is not an experiment that we did. This was done in somewhere in Edinburgh or some other place. This is publicly available data. What we have here is measurements in microvolts on the scalp. So there are 32 electrodes or so on the scalp, and we are recording measurements of electrical signals in microvolt units, right, as a function of people reading sentences on the screen. So they might read a sentence like, "It was a breezy day outside and John went out to fly a," right? So you're predicting at that moment the word kite, right? You're not predicting the word aeroplane. So if you see on the screen the word kite, then you're not surprised. But if you see the word aeroplane when you were expecting kite, then you're greatly surprised. So you can actually do a sentence completion study. For each item, you can get a measurement of how surprised a person might be if you show them a particular continuation like kite or aeroplane and so on, right? You can get that measurement for each item in your experiment, and from that you can calculate a close probability, the probability of producing that particular word like kite or something like that, or aeroplane, and you could center it as usual, right? I always center the predictor, so you could have a centered close probability as a predictor for the electrical signal on the scalp. Right? So what we are doing is we are trying to determine, the scientific question we're trying to answer is when there is an increased or reduced probability, right, of producing a particular word, you are more surprised, and so the electrical signal will have a greater amplitude. That could be one way to think about this kind of thing. So basically the point is we have some dependent measure, a continuous variable in microvolts, and we are looking at the effect of centered close probability on this dependent variable, right? It's just like the usual situation, except there is one very important twist now that we are going to pay attention to. This twist was there in previous data sets too, but I just ignored it, right? But now I won't. We have repeated measurements from each subject. We also have repeated measurements from each item, but let's not talk about that right away, okay? So what's interesting here is that because I have repeated measurements from each subject, the independence assumption of the simple linear model is now being violated, right? The residuals will no longer be uncorrelated, right? So that's the issue that has to be solved in this kind of repeated measures data, right? And the issue is solved by fitting these so-called linear mixed models or multi-level models, and in the Bayesian framework we generally call them hierarchical models, right? So this is what the data look like. So this is on microvolts, right? And you're seeing the distribution of the signal, right, in microvolts, and you can see that it's roughly Gaussian, right? So we can work with the Gaussian likelihood. It should be good enough for this kind of thing. Reading times are different than this. There you generally use some other transformation, like a log normal or something, but here we can work with the normal distribution, right? So what's interesting now is that we are still going to fit a linear model, right? Nothing changes. Everything that we did so far, we know we will do the same again. We have the signal as a dependent variable, assume a normal likelihood, assume an intercept just like before, assume a slope just like before, and the slope is going to be multiplied with a centered close just like before in order to get the effect of close on the dependent variable. However, one interesting twist now is that there's all these weird terms here. There's this term here and there's this term here that is new, right? This is no longer a simple linear model. This is now a linear mixed model or a hierarchical model. And what's going on here is that think about what alpha represents. Alpha represents the average signal. When the predictor is centered, alpha is the average signal, right? The magnitude of the average, right? So what the first term here, the u sub n1 is doing, for every subject in the nth row of the data frame, small n represents the row ID in the data frame. I look up the row ID in the data frame, and whatever the subject ID is in that particular row, I take that row ID, and that's that subject's ID, right? So for subject I, let's say, some subject 1, for example, right? I'm adding an adjustment, which I'm calling u sub 1, right? I'm adding an adjustment to the grand mean intercept for that subject. So the assumption here, graphically, the assumption here is that there will be some grand mean value. This is the grand mean value for the intercept, right? And some subjects will be slower than the grand mean, and some subjects will be faster than the grand mean. So for example, if subject 1 is slower than the grand mean, then subject 1's first subscript refers to the subject, and the second subscript refers to the fact that I'm talking about the intercept adjustment. Okay, then if the first subject is slower than average, then that subject's u sub 1 1 is going to be positive, right? If this subject, let's say subject 2, right? Subject 2, let me just redo this. This was subject 1. This is subject 2, right? So this subject is faster than average, right? Then this guy's adjustment will be negative. And if some subject has the same average response as the grand mean, then that will be his or her adjustment would be 0, right? So what we are doing is we are fitting a simple linear model, right? We've got the response, we've got the alpha, right? Alpha term, the grand mean, and we are adjusting it for each subject. We are adding an intercept adjustment, right? So this will give you a new term in the linear model, and this new term is actually going to introduce a new source of variance in the model. And what is that source of variance? By assumption, I'm going to assume that the adjustments to the grand mean intercept are coming from a Gaussian distribution with some mean 0. So that means on average the adjustment will represent the grand mean, and some variability which I'll call sigma u1. So what I've done is I've added this source of variability in the simple linear model to represent the fact that I have some potential between subject variability, between subject variation in what? In the intercept. Some subjects are faster than average, some are slower than average, right? So that's that detail that I'm now representing mathematically in the model, okay? So that's this term here. Now the other interesting term that extends the linear model is this term here. This term basically is representing the following situation, which I'll again illustrate graphically, right? So think about this situation. So imagine that I fit a simple linear model, just a simple linear model with one intercept and one slope, looking at the response as a function of centered close or something, right? So 0 could be here, for example, right? So this would be the intercept, and then the slope tells me what the effect of close is, right? So what's interesting is that different participants might have different effects of close probability, right? So some participants might be like this, some participants might be like this, so some participants might be flatlining, right, without any effect of close on the response. So they could be between subject variability in the slope as well, right? And so that's what I'm trying to represent in this model now, right? I'm representing the possibility that there will be between subject variability in the slope as well, right? So that's why I added this term here. So what's really cool about this is that now I've added two new sources of variation in the data. One was the residual, the standard deviation of the residual, right? The other is the between subject variability in the intercept adjustments, and the other is the between subject variability in the slope adjustments, right? And so these are the two new terms that you see here. One is U1, the other is U2, and they introduce two new variance components. I've written tau here, right now I wrote sigma, it doesn't matter what you call it, right? So basically there are two new sources of variability in this model. And what's really important about this is that these two sources of variation are now taking care of the fact that they are accounting for the repeated measures nature of the data. As a consequence, the residuals, the epsilons in the linear model will now be completely independent and identically distributed, right? But any kind of correlation in the data will be taken care of through these terms in the model, right? In the earlier models, the linear models with the normal likelihood and the log normal likelihood, I was ignoring the violation of the independence assumption. And as a consequence, if you were to look at the residuals of the model, you would see some correlation in the residuals. So that assumption is violated. Not anymore, right? So we've taken care of that. And so that's what this model looks like now. I've defined some priors as usual. I won't dwell on that too much now, because by now you should have a pretty good idea of how prior specification is done through prior predictive checks and so on, and sensitivity analysis and so on. So these are reasonable priors for this kind of normal likelihood. And basically now I could elaborate this model even further, right? So there are many more elaborations of this model possible, but this is already a huge step, because this takes us beyond the linear model, the IID assumption that one normally has in linear models, and it allows us to model repeated measures data, right? So that's a huge advantage of this approach, right? So as I mentioned, there are three variance components now. So if I look at the posterior distributions, so these are my prior specifications, as I mentioned earlier, and this is the model fit is very straightforward, okay? So what has changed now is that what has not changed is that I have a simple linear model specification here, just like before. The intercept, as you know, is implicit in a linear model specification, just as in R, in LM, in the LM function, you can drop the intercept term, right? So, and it's implicitly understood to be there. It's the same in the BRM function, right? And the other thing I've done here, this thing that I've added here in this syntax, this additive term here, this is the term that's adding the intercept adjustment, which is again implicit, and the slope adjustment, right? The U1 and U2 terms are being added here. And this double vertical bar means that I'm assuming that the U1 and U2 are completely independent of each other, right? So I could, of course, relax that assumption and assume that U1 and U2 are correlated to each other, right? All that I would have to do there was a very small change, right? Mathematically, what would I have to do? I would just have to assume that U1 and U2 are coming from a bivariate normal, right? So if you cast your mind back to bivariate and multivariate distributions, right? So then what would happen is the means of these two would be assumed to be 0, and then there would be some variance covariance matrix, which is, how did I call it? I have forgotten, tau. What is it called? Tau U1 and tau U2, right? So let's go back. I've got tau U1 here on the diagonals. I've got the variances for the two elements, so the intercept and slope adjustments. And on the off diagonals, I've got the correlations, right? So I've got, so I think I messed up this terminology. So let me just fix that quickly. The terminology, I'm using tau instead of sigma here, right? So let me use that just for consistency. So I've got tau U1 squared, I've got tau U2 squared on the diagonals, and I've got the correlation between the intercept and slope adjustments now assumed in this bivariate distribution with tau U1, tau U2, right? This is all discussed in the lecture notes, of course. So you can look at those if you're interested. I just wanted to introduce the model to you so that you know how you would put together a more elaborate model that assumes a correlation between these two terms. So then the model will look like this. Instead of writing the double vertical bar that I showed you earlier, this double vertical bar, you would write a single vertical bar here, and that would express the fact that you're assuming correlation between the intercept and slope adjustments. And what that means You know, when you define assume such a correlation, what it means is that you're either assuming that there is some positive or negative or maybe no correlation. You don't know whether it's zero or non-zero, but you're assuming that there's some kind of correlation between the intercept and slope. If there was a positive correlation, it would mean that the slower the subject's intercept adjustment, the bigger the subject's intercept adjustment, the bigger their effect of closed probability, right? So that's what it would mean. And the negative would have the opposite meaning, right? So these are things that you can include in the model. Very easy to do with this 1 plus C close single vertical bar subject would take care of that problem for you, right? Take care of that assumption in the model. Of course, you've added one more parameter now in the model, which is the correlation parameter, and that, of course, you would have to take into account and define the priors on and so on. All that is discussed in chapter 5. I just wanted to give you a look into all the interesting action that can now unfold. Now that you know the basics of Bayesian modeling, you know how to do prior predictive, posterior predictive checks, and how to interpret posteriors and so on. So these are the important skills, and understanding conceptually how these models are put together. These are the important things that I wanted to get across. And now transitioning to hierarchical models is going to be relatively easy, because all that will happen is that we'll just keep adding more and more parameters and more structure in the data, right? So that's coming up in the subsequent chapters in the book. Now, just to close up, I just want to show you the posterior distributions of the parameters now. So what we are looking at here is the alpha parameters. This is the grand mean, right? Then we are seeing the grand mean slope parameter. These are often called fixed effects in the frequentist world, right? And here we are seeing the standard deviation of the subject intercept adjustment. So the tau u1 that I mentioned earlier, right? And this is the standard deviation of the slope adjustment by subject, right? So you can see that this is quite large here relative to the intercept adjustment. So these two are pretty similar, right? In fact, it might be slightly larger, the slope, which is interesting because it shows that there's important variation between participants in the effect of their clothes on their response. And here's the sigma, the residual variability. So now we have 3 sources of variance, 1, 2, 3. These 2 are the between subject variances, and this is the within subject variance, right? So standard deviations, of course, right? So basically, this part is just like the linear model. Nothing new there. What's new is these 2 terms here, right? And you can keep elaborating this model as I mentioned earlier. Okay, so more details will be in chapter 5 if you want to look at those. And I would strongly advise you to go and look at the other chapters that start after chapter 5, because I unpack a lot of details. We unpack a lot of details there about how to think about priors, how to elicit priors from yourself or from experts, and how to do more complex models like building computational cognitive models and mixture models and multinomial processing trees, and all kinds of interesting tools are now at your disposal now that you understand the foundational ideas of Bayesian inference.